And I am terrible with names. I know this is Doohickey. Kyle, right? All right, I remembered one. This is Chantel. I'm just guessing. This is Penny. Denise.
Yep.
Howard. Stephen.
It's right there.
That I like that. I like that. And this is Chris over here. This is Rick. And I'm Jeff. So anyway, it's good to see you all back on this hot day. And I think last week I told you I was going to give you a few handouts. And Rick, can you give me a hand with those?
Yep.
Thank you. First one that I'm sending around is the radio spectrums. I actually found that I have the manual on a Kindle, so it's very easy for me to print those out since I can get onto it digitally. So.
Frequency spectrums, or is that the most chart?
Yeah, it shows all the different spectrums.
Yeah.
You can give Chris one.
Wait a minute, you can print off your Kindle?
I actually uploaded onto my computer.
Oh, I see.
And then I printed it.
Yeah, okay.
So, all right, so there's that one, which if you remember, that's everything, where our spectrums are. Thank you, Rick. You know I need the cheat sheet. And while you're up, if you could hand those out as well. So what Rick is handing out now is the radio frequencies, the different bands. And so these are always good to have. Whenever you're operating radio, I always have one of these close by, just so I can make sure where I'm at and make sure that I'm in the legal range and not subject to that $37,000 fine from the FCC.
Is there any reason why we have two?
You can never have too many.
Oh, okay. All right. Okay.
I have 4 strung out.
Okay, all right.
I can't afford $37,000.
No, neither can I. All right, so last week we got to the point that we didn't quite get all the way through the chapter, so I want to cover just a few other things very quickly before we get into chapter 3. But we got a lot to cover in chapter 3 today. So, radio signals and fundamentals, how a receiver sees the radio spectrum. As you look here, we see that there's different strengths. The signal strengths up and down, right? So there's strong signals, there's weak signals, and in between those, you get nothing but noise. What does noise sound like?
Like the white noise?
Like the white noise, crackly, and there's nothing. It's like there's nothing there, right? And occasionally you can get some signals that is down in the noise, and you can actually hear them. A few weeks ago, it might have been a couple months ago now, we were out doing a POTA. And Rick got his first POTA contact, which is Parks on the Air. And he was on there, and there was a guy down in Mississippi. And we were out at a park, and Rick is just trying to get this guy that's in Mississippi. Rick can hear him, but he's really weak. He's really in that weak, noisy signal area. And finally, after, 5-10 minutes of trying.
Took a while to crank up 98 watts when I finally got in there.
So Rick cranks his radio up, and he sends him a signal, and the guy gets him. And the guy was, what did he report to you, about a 3.3? Which a 3.3 signal is, man, you're hard to hear, and I can barely make you out.
You're one step above.
Yeah, but he made the contact. And so you can make contacts in that area, but it's much, much easier to make a contact when you got a strong signal and you're hearing a strong signal. As we talked about last time, radio waves are, they go the distance, and it can be calculated, at radio waves travel at the speed of light. Exactly. That is on the test. It's on the new test. It's on the old test. It's on the test. So that's something to remember. Now, as we talk about radio equipment, we're going to get into a little bit of radio equipment. We'll just start a little bit tonight. You have we'll talk about the basics. You get a transmitter, something that transmits your signal. It takes your signal and it moves it into the antenna, and then it sends it out. That's a transmitter. Then you got a receiver. Takes some information, or the signal that's coming into the antenna, and you receive it, and it converts it so you can hear it. That's a receiver. You put the two of them together, you got a transceiver. And so if you've ever heard the word transceiver, it's something that transmits and receives. And most of your radios are transceivers. I mean, you can get some radios that just receive, but your FM radio in your car, it's a receiver, right? It's not a transceiver. But your ham radios, they're going to be transceivers. And a repeater. We talked a little bit about repeaters. I know the question came up last time. What is a repeater? A repeater, basically, you end up with a transmitter that transmits your signal, goes into what's called a duplexer, and then it goes up into your antenna, gets out, and it transmits on a different frequency. And it transmits it farther. So you can extend your range by running through a repeater. So it takes your signal and it repeats it, but it just repeats it on a different frequency. And those are, yeah.
Why does it do a different frequency? Why not the same?
Rick, why does it put it on a different frequency?
What? Let's see. Oh, you're talking about the split, right?
Yep. So you.
Well, you don't get feedback. And if you keep on the same frequency, 147.015, most soon you'll see that simplex. But at the same time, this system, the split is there because of where this thing is located, the power it generates, and the area of coverage that it can do. So you don't interfere with anybody else.
Basically, a repeater is two radios inside of a chassis, and what will happen is it will simultaneously, as it's receiving your signal, it will turn around and put that out in the transmitter. And so that's another reason that you have the duplexer in place, is because if you didn't have that in place so that you didn't get interference, you'd have to have two separate antennas, one for transmitting and one for receiving at the same time.
It essentially transmits to itself.
Yeah, I was just thinking it probably makes sense.
If you are on a
It
frequency,
needs to be two different operations, and if you're doing the same frequency, I get you.
Yep.
Yeah, okay.
Yeah.
if you're on one frequency, the person who's sending the message to the repeater will tell you what the new frequency is.
The way the repeaters are set up is they have a set receive frequency and a set send frequency. So you actually program your radio to automatically transmit on this frequency and receive on this frequency when you're hitting that repeater.
Doesn't change at all.
Nope, it's always the same. Yep. Excellent questions. Okay, so tonight we're going to cover a little bit about electricity, components, and circuits. And this is an area that can get very deep, very quick. And I am not an electrical engineer. Just to give you my background, when I first started in college back in the dark ages, as my daughter would say, I started out thinking I was going to be an engineer, a mechanical engineer. I started getting into the math and into the higher math, and I'm thinking, This isn't for me. And so I became a bean counter. I can count beans. 1 bean, 2 bean, 3 bean, right? Jack and the beanstalk, right? So I'm an accountant. I use math in my work, but nothing like they do use in electricity and mechanical engineering. So I am no expert by any means. Okay, so my disclaimer there. But I will try to get us through what's going on. But before I do that, Rick, I got something else to pass out.
Okay.
You can pass out one of these. I think 1, 2, 3, 4, 5, 6. Yeah, we got enough. I think I got 11 copies there. So what I've done is I have grabbed from the test pool, the new test pool, and I've gone through our chapters that we're studying and grabbed the questions that are going to be covered based on the chapter that we're covering. You're going to see we're not going to answer all of these questions tonight, but all the questions are here, and if you look very carefully at these questions, I gave you the answers. And that's the way the ARRL does. They give you the answers to the questions so that you know what's going to be expected. So anyway, so I've got those for the week 2 and week 3. There were no questions for week 1. Week 1 is just strictly introduction. So there are questions from week 2 and week 3. All right. So as you look through those, I think the green ones are for the stuff we're covering tonight. Yellow ones were from week 2. That's the only way I could keep them straight when I was pulling them, was to color code them. So what we're going to cover this evening, we're going to cover some of the fundamentals of electricity and circuits. We're going to cover voltage and current, resistance, capacitance, and inductance, reactance, impedance, and resonance. Woohoo! All these ANSYS words. I can't keep them all straight. Sometimes. But as we walk through them, hopefully we'll be able to. And common types of electronic components and basic radio circuits. So those are the things that we're going to try to cover this evening. And that's a lot. We'll see how far we get. But we'll keep it rolling. So current. What is current? The answer's right up there. The flow of electrons through a wire or current. So it's what can kill you. Absolutely, Rick. It is. All right.
What did you say?
It's what can kill you.
Current can kill you. So you have.
I was told amperage could kill you.
Yeah.
That's part of it, and I'll show you why.
And I'm not an electrician.
You got a pacemaker, it don't matter.
I hit a highlight pole one time. I should have been dead, but I'm here.
I'm glad you're here. I'm glad you're
I
here.
am too.
All right, so when you think about the elements, and I remember this from my mechanical engineering and chemistry classes, there's this great big long element chart that had all kinds of different elements and how things worked. But there's protons, there's electrons, and there are neutrons, and they all interact with each other. And the thing to remember about current is it's the electrons that move through a wire or something else that causes current. And current is measured with an ammeter. And an ammeter measures amperes.
Say that again.
An ammeter will measure amperes, just like you had mentioned.
So that's amplitude.
No, amplitude is different.
Oh, okay, I thought the sound, the word was similar.
Okay, so electrons are negatively charged particles, where a proton is a positively charged particle, right? So this is a negatively charged particle. This is a positively charged particle. This one doesn't have a charge.
What is the last one? I couldn't.
The last one is a neutron that has no charge. It's not positive or negative, it's neutral.
All right.
The symbol for current is I. I stands for current.
Uppercase?
Yes, uppercase. And it's measured in units of amperes, which has a symbol of A or amps. So far, pretty logical, right? Now we get over to voltage. And I remember as a kid, grew up out in Utah, and the electric company out there, they always had Ready Kilowatt, which was a little dude that and he would have lightning bolts coming out of his arms and his legs, and he was Ready Kilowatt. So I always remember kilowatts and voltage. So voltage is, what is voltage? Any idea? I haven't got the answer up there yet. Let's see. It is the potential force that makes these electrons move. So if you have electrons sitting there and you don't have any voltage, are you going to have any current? No, you won't. There has to be voltage in order for your electrons to move through that wire in order to have current.
I'm sure you're going to approach this too, but you have to have ground
Yeah, you do.
that you're coming up to that.
Yeah, we'll get there. Okay. So voltage positively charged. It's represented by the symbol E. And it's measured in volts plus or minus. And it's measured with a voltmeter. Pretty standard stuff so far. And it's always from one point to another. Or to the ground. So,
Question on
yes.
the prior thing.
Yes.
You said it was positively charged, but then you have measured in volts plus or minus, so sounds like you can have negative volts, or what
You technically can, if basically the wires are reversed, it's gonna show up on meter as a negative voltage, just because of the way that the meter reads it.
Reverse polarity?
Yep.
Is the negative maybe receiving volts?
Yeah,
Yeah.
basically, if you would hook a multimeter or a voltmeter up to your wires, if you're wondering why you don't actually, or why it's reading negative voltage, that usually means that your wires are crossed.
Yeah, well, I know with batteries, they get with positive and negative.
And the funny thing is, I watched a YouTube video from a guy who's a master electrician, and I always thought that if, when it runs through the wires, I always thought it was positive to negative. And he said, actually, on most batteries, it goes from negative to a positive charge.
Oh,
So I think the next slide will help to solidify this. This gets a little confusing. It's confusing my mind. So let's take an example here. So here we have a pressure. We have pressure here, okay? And that pressure comes in a pump. A pump is driving pressure, okay? So as the pump winds stuff up, it's pushing it along, right? It's pressure, and then it causes, in this case, it'd be water, let's say. It's causing the water to flow around in a circle. Now when we come over here, we got a battery. And we're applying voltage. So out of that battery, we're getting current that's driving around and moving through that wire. So you got voltage and pressure. So if you think of water, there's got to be something that's making it pressurized to move. The same thing with electricity and current. You have to have something that causes that electricity to move. And that is where your voltage comes in. Now, when you're thinking of current, there are a couple of types of current. There is direct current and alternating current. Anybody ever heard of those? Direct current and alternating current. Okay? Rick has. Excellent. So, current that flows in one direction at all times would be, what do you think? Direct current. Absolutely. So, direct. Think it goes from here to here, right? It's direct. But what about alternating current? Well, let's go on direct current. It can include batteries, solar cells. These are all direct current. And when we come down to current that regularly reverses direction, that is alternating current. It goes from this direction to this direction to this direction. That's where we have the household current. That right there, that plug, that's not a direct current plug. That's an alternating current plug. I would play with the one on my computer, but we don't want my computer to die because my direct current in my computer doesn't work. So I have to have alternating current going to that computer or it's going to die. Okay, so household power is alternating current, radio signals in the megahertz and gigahertz range. Voltage that regularly reverses direction. Now we're talking voltage here, is AC voltage, and voltage that has the same polarity all the time. So when we're talking regularly reverses, it's going from plus to minus, plus to minus, plus to minus. Okay? Same polarity, it's always plus, right? And here's just a schematic showing the direct current and alternating current. Your direct current, that bottom line, is if you didn't have any pulses in that current line. It's always just going in a straight line. The other one, it's still going the same direction. It's not alternating, but it's, high, low, high, low. But then we get to alternating current. It goes up, it comes negative, goes up, comes negative. And that's alternating current. Any questions so far?
What was confusing for me was batteries, direct current. When you did, right now I was going to say, in parallel, what's the other?
Series.
Series, yeah, because you're going to reverse, so to speak, you're going to go negative, positive, negative. That's always what confused me. Series.
Yeah, it can be confusing. Now, if this has been confusing, I hope it hasn't. Just wait. Yes.
Originally, I didn't have a question. I keep looking at your diagram and talking about direct and alternating. I understand the difference, but in your diagram to the left, it's got square corners, and they're not even. Is that what is that to represent? I have no idea.
Yeah, that's representing pulsing within that direct current. You might have some spikes in it, but
Direct current, you might have
you could,
spikes.
yeah, you could have some spikes in it, but as you see, it never drops below the line. So it might drop to 0, then it'll come back up.
Basically, that's a picture where you would hook, if you hook a battery up to an oscilloscope and zoom in on it, that's the way the signal would actually appear on the oscilloscope. So there is some fluctuation in the voltage when you're using the equipment, but it's not like AC.
Yeah.
Yeah, it's not like AC where it's alternating back and forth.
Alternating is more consistent,
Yeah.
where direct can have spikes.
It can. Depends on your source. I mean, if you've got a solid battery source, then you're going to look more like the line on the bottom. It's going to be more direct, just straight. If you've got a battery that might be a little bit weak, you might have some spikes in it.
Or another way that you can look at the spikes too is like if you would key up, basically if you'd be just monitoring or listening to the radio, and then you go to key it up.
It's going to draw more. It's going to put more voltage to it. So, excellent question. All right.
What's this? Series and parallel.
Series and parallel, yeah. Circuits. So we're going to talk a little bit about circuits, and I'm just trying to figure out where I am in the book because it just went out of order. And that's my own fault because actually I just turned too many pages, that's all. Okay, so circuits. Any path through which current can flow through components is a circuit. You have series circuits. So the current is the same through all the components, and the voltage divides amongst the components. And this gets confusing. Rick gets confused with this, so do I. But the theory is that your current is the same through all components in series. And when they talk about series, it's like Christmas lights. That's an excellent example. It's the top picture there. It's coming up. It goes through one component. It goes through the next component. It goes through the next component. That's a series. One right after the other.
Your amps increase. No. Current is amp is the same voltage increases.
Diesel mechanic. I was a lineman. We were up in an aluminum basket. We were up doing the power line up here. There was a underbuild below us. We were in an aluminum basket. My buddy was working over here. I was working over here. Basket's smaller than this table, so we're trying not to touch each other to create that
closed circuit.
That closed circuit.
Yep.
But then we're working, and then our knees touch, and we both just drop.
Y'all were parallel.
And we learned not to do that.
Don't be in parallel.
Yeah.
Excellent example, but you're right. It's not something you want to have happen.
No.
Okay, so copper is a good, steel is a good conductor, aluminum is a good conductor.
I think actually silver is also it's too expensive to use.
Yep.
But it is used in technology.
Yeah.
Now
Yep.
with the transistors.
Sure. Yep. So good conductors. These are kind of, this will be on the test somewhere along the line too. What's a good conductor? Also, what's a good insulator? What do you think a good insulator is? We'll prevent. What happened to rubber? Okay. I hear wood. Yeah. What else? Glass. Plastic. So let's see what we got. We got glass. We got rubber. We got non-metallics. Okay. And All those other stuff all in that non-metallics. So how do you measure resistance? An ohmmeter. You betcha. You bet.
What was it?
It's an ohmmeter.
Remember Ohm's law?
Ohm's law, and we're talking about resistance. And so we measure it with an ohm meter, and it's measured in ohms. That guy's got his name all over the place.
He was the inventor of Ohm.
It could. But anyway, what is Ohm's law?
So we are going to use the circle, the power circle. Never mind.
We will.
Oh.
We will. Okay, so Ohm's law. This is the relationship between current, voltage, and resistance. And within your question set, you're going to see a lot of questions that have to do with if we have so much current and we know the resistance, what is the voltage? Or if we know one of those three, we can find the other. And this is through simple algebra, which
Great.
Did you just say a cuss word?
algebra, or as you would call it, algebra. Okay, so what we got here is we got voltage on the top, E, and we've got E over I and R. So the thing to remember is ohms times amps equals volts. Okay? So ohms is R, right? Amps is A. I, yes, it is I because it's current. So we got.
Hard to do it 7 feet up.
It is hard to do it 7 feet up. All right. So we've got voltage, which is E, equals volts equals amps times, yeah. That's,
I times that. That's all thanks to Bruce Letter.
yeah. Current,
Personally, I think it should be A as well. Makes sense.
because that's what you're
Yeah.
measuring it in. Okay. So E equals I times R, or said another way, I equals E divided by R, and R equals E divided by I. But if you know this one here, you can get to this one and this one.
Another way for those that are mathematically challenged or more hands-on, basically if you draw that triangle and then cover up whichever one you're looking for, that will give you that'll give you the formula for either one. And the two on the bottom, you just multiply those together, and then if you're trying to get the one above with one below, it's the basic division sign, or
Yeah.
division sign.
Oh,
So-
E over I times R is equal to 1?
Kind of, yeah.
Yeah, okay.
So if we have, let's run through a problem. I want a problem I have an answer to. Look at you.
It says I'm the problem.
Well,
Everything you've given us in the last 2 weeks is a problem.
everything I've given is a problem. Yeah.
It's a lot easier than you think.
It,
And then I have to stop thinking, and then I get it.
There's lots of calls.
Thinking I can't get any of it.
okay, here we go. Let's see how we do on this one.
Don't be doing no E equals MC squared stuff.
Yeah, no, I won't do that one. Okay, so we've got current, which is I, right? Current is I, and that equals 3 amperes. Okay? And we've got voltage, which is E, is 90 volts. So our resistance equals how many ohms? Any thoughts? So we're trying to solve for R, right?
I know.
We're solving for R. So I equals, we're solving for R, right? So that equals E divided by I. E is what, 90? Divided by 3 equals 30. Does that make sense?
30 ohms.
30 ohms. What I did when I was getting ready for this test is I just took that formula and just memorized. I memorized this formula, and then I went like this. You know, what am I missing? And how does that fit into here? And then you solve for your blank. That's the best way to look at it and the best way to go after it.
The test will give you those figures on the right. You know, it'll give you.
Yeah, the test gives you these, and it's asking you what that is. And then it'll give you 3 choices. The 3 choices for this one are 3 ohms, 30 ohms, 93 ohms, or 270 ohms. So if you times those 2 together, you get the 270, which that doesn't work. 93, you add them together. That one you can throw out immediately because you never add them together for this. So it's easy to throw that one out. And if you come up with 3,
10, you already got 3.
you already got 3, so that doesn't work either. So you can almost do it by process of elimination to get to your 30. But it just takes practice. And if you go through all of the questions that are here that relate to that, you'll be all right. You'll be fine. Just make sure that you understand how it's calculated, and you'll be able to do that. Or you can memorize, if it's got a 4 and a 12 in it, it's going to have an answer of 3. There's a couple of ways to approach this, but the best way is to understand how the formula works. Okay, so we're going to take this on to another step forward, and we're going to talk about power. Oh, power. You know, everybody likes a little power, right? Same type of formula. We've got power equals voltage times current. So P equals E times I. And if you remember, P equals E times I, and power is measured in watts. Voltage, which is E, is measured in volts, and current in amps. And you can do the same type of thing with that. It's just an algebraic equation to solve for one or the other. Chantel, are those proper algebraic equations according to the high school? All right. Okay, so there's a number of questions in there on power as well, but they all use that same formula. And these guys, when they put these tests together, they don't usually try to trick you. They don't put trick questions in there. They're straightforward.
Some are pretty blank, you know what they are.
Yeah.
I.e. like the one we just went through here.
Yeah. Yeah. Pretty straightforward. Any questions so far? Have I lost everybody?
No, everybody
Cut-
has to grasp.
I'm sure I've lost some, and that's
Basically, watts and amps are the same thing, only different value.
yeah, different value.
It was 1,000 watts equals 1 amp.
So
It'll all depend on the.
so if you
on the voltage.
so if you think about it, that's a very good question. So in our formula, right? We got power equals voltage times current, which is I. So this is where your amps come in, right? This is where your volts come in. And this is where your watts come in. So in order to get your watts and amps, there's your volts in between. So they relate to each other, but they have to have this voltage applied in order to get there. All right. So this is a chart that kind of shows the power relationships. And it's basically talking about that same equation. E equals I times R to come up with what our answer is. Ri equals E divided by R, and R equals E divided by I. Just gives us some examples of walking through that same equation. All right. Now we're going to go a little bit into components. So each component in a circuit, which is where your current's flowing through that circuit, right? And there's components in there. They each perform one or more functions. They either store energy, they use energy, they route the current, they amplify a signal. Each component has one or more purposes. A resistor is one of the components that we'll talk about. And just from its name, and I know the answer's up there, but just as you think through that, a resistor, like a teenager, resists, right? It's trying to push back. So a resistor opposes the electrons, the flow of those electrons in a circuit. And as it's opposing those electrons in a circuit, it's losing some energy. And that energy comes out in the form of heat. Must be a lot of resistance going on outside today, because we're getting lots of heat. So if you think about it, like water in a pipe, right? If you got something that's blocking that flow of water, it's resisting it, it can heat up, right? And it's measured in ohms. Another component that we have is capacitors. And these store electrical energy in an electric field created by a voltage created between two electrodes separated by a dielectric insulator. What I like to think about on capacitors is they store energy. That's what they're for. And when we're storing that energy, it's called capacitance. And it he looks like a diagram, something like this, with the different symbols for different components. And then this is just a chart of the symbols that are used in those schematics. And then you can get oscillators and amplifiers. Those are other components that we can use. And we can end up with modulation. We'll talk about modulation as we get into how the radio waves come together in your radios, along with mixers. So a mixer converts a radio signal from one frequency to another. Don't confuse the mixer with what you're doing, what you've heard with your stereos, right? It's a different kind of mixer. It's not like you're trying to get a stereophonic sound, but you're trying to take a radio signal from one frequency to another.
So is that what the repeater does?
Is that what you're talking about with
You were
repeaters?
saying it takes one frequency and transmits it.
It's a kind of a different concept. And that's what I have for you this evening. Next week, we're going to be talking about propagation, antennas, and feed lines. We're going to get more into the radio itself. And the electricity, I admit, is dry, especially when I'm teaching it, and I apologize for that. But it's some deep stuff. And I'm thinking if we have an electrical engineer that's teaching him, maybe he's got some. But I like your story. I like that story. That's a good story.